The proof is very technical, using lower continuity arguments. That is a technique on functional analysis. So in this talk I will comment about that result, but using a geometric approach for the proof based on the Palais-Smell condition that is more geometric instead of analysis. And mainly in the talk I will show how to apply the results for engineer applications. Yes. So my motivation is interpolation problems. Let's begin with interpolation on R. We have some given times, T1, T2, Tn on R, some positions denoted by P1, Pn, and velocities V1, Vn. An interpolation problem consists of finding a curve, gamma, such that gamma at those times gives the corresponding positions, and gamma dot, the velocity, at those times gives the corresponding velocity. So one can solve the problem by interpolate pair of points with polynomials and glue pieces of polynomials together. Is what is called splines in numerical analysis. And for that, we need polynomials of degree greater than or equals 3 to solve the problem. And a basic way to solve the problem is to use cubic splines, because they are natural in the sense that they minimize this cost functional. So if you are working on control problems, for instance, and you have a double integrator, that means u equals to q double dot, you are minimizing the control effort. No? My motivations come from robotics and control systems, in particular path planning, because we can design trajectories by interpolating points or avoiding obstacles in the workspace. And if we want to talk about path planning, one application is interpolation set of node points in the configuration manifolds, where the configuration manifold usually is a Riemannian manifold. And in that sense, we wish to minimize the energy consumed along trajectories, as I commented before in the case of R. And also, in addition to minimize some quantity like the energy, we want to complete some task, like avoid an obstacle in the workspace, or prevent collision if we are working in a multi-agent system problem. For that, for both applications, obstacle avoidance and inter-agent collision, one can use artificial potential functions in your functional to minimize in order to avoid the obstacle or avoid the inter-agent collision. And in this talk, the principal goal is to show a rigorous framework to study path planning problems and provide safety guarantees in obstacle avoidance tasks. That means how to design the potential functions in a smart way in order that you can avoid the obstacles that you have in your workspace. So let's begin with the plural statement. We assume that Q is a complete Riemannian manifold. QA and QB are points on Q. BA and B sub B are tangent vectors at the points QA and QB of the manifold Q. We will denote omega, the space of Sobolev class H2 of curves satisfying these boundary conditions. Q at A equals QA, Q dot at A equals BA, Q at B equals to QB, and Q dot at B equals to B sub B. And we denote by B a smooth non-negative scalar field on Q that we call artificial potential. And we define this cost functional, this action functional J from the space of curves omega in this way, where B is the artificial potential and dt denote the Levi-Civita connection on Q along the curve Q on omega. Yes, and the problem consists on find and study the minimizers of J. Yes. So in order to study the minimizers of J, one can find first necessary condition for optimality, that is the condition of critical points. And then we have this result that the curve Q on omega is a critical point of the action functional J, if and only if Q is smooth on the interval AB, where is defined the action functional, and satisfy this four order equation here. Note that you have these three of Q dot, so you have a four order derivative, covariant derivative, R denote the Riemannian curvature, and grade of B is the gradient vector field of B with respect to the Riemannian structure on Q. Yes? In the case that B is equal 0, we have the usual Riemannian splines that are well known in geometric mechanics, studied by Peter Crouch and Fatima Silva Leite. When we have the potential function B, we call smooth solutions of this equation modified Riemannian cubics. And this result was obtained in this paper together with Tony Bloch, Margarita Camarini, and myself in the proceedings of CDC in 2017. And also we studied this kind of necessary condition for optimality in this paper with my PhD student Jacob Goodman, where is the main content of this talk here today. So the next question, we have necessary condition for optimality. The next question is, when do global minimizers of J exist on omega? Yes, this is what we prove in the paper of GCI, as I commented before, using lower semi-continuity arguments, using functional analysis techniques. But now I will show how to prove global minimizers using Palais-Snell condition. So suppose that M is a Hilbert manifold with a Riemannian metric, and F that goes from M to R is a smooth functional. Yes, in our case will be J. Yes, we say that F satisfies the Palais-Snell condition if every sequence Qn on M, for which the absolute value of F at Qn is bounding and the differential of F at Qn in norm goes to 0, with the norm induced by the Riemannian structure, has a convergence subsequence. So we wish to apply this result in our context. So this is the theorem of Palais-Stern that supposes that M is a Hilbert manifold which is complete as a Riemannian manifold, and F is a smooth bounding from below and satisfy the previous Palais-Snell condition. Then we can guarantee that there exists some X such that is the minimum for our functional. No, F at X is the infimum over the M's on the manifold, on the Hilbert manifold M of F at M. In our case, omega, the space of curves, is an infinite dimensional Hilbert manifold modeled on this space, and omega is complete with this Riemannian structure. So we can define a Riemannian structure for which omega is complete. And also J is smooth and non-negative on omega, where the conditions of B about that B is positive is crucial to show that J is non-negative on omega. Then, given this, we can say that J satisfies the Palais-Snell condition on omega, and then we have the existence of global minimizers for our variational problem. This is an extension of this paper of Jimbo, Gignone, and Piccione. And as I commented before, one can show this using other techniques that are not related with geometry, but since this is a conference of geometry, I wanted to show the proof of the theorem in a geometric way. So now for what helps the function B? Now, for me, as I commented before, we will use the function, the artificial potential B, to avoid an obstacle. So in general, an obstacle can be a subset of the manifold Q. I will start with point obstacles and then extend the results to general obstacles. So to talk about obstacle avoidance, we need to define three kind of regions given three real numbers R, R star, and capital R. We can define the collision region as the red region here, the risk region as the yellow region, and the safety region is the blue region. And we say that Q on omega avoids the obstacle P with tolerance R if Q of T is on Q x minus the collision region for all T on AB. That means it's on the risk region or the safety region. And the key is how to design now B in order to provide safety guarantees, in order to avoid the obstacles safely. So for that, we will call a curve in omega for which Q of T belongs to the safety region a reference trajectory. And as I commented before, first we will study the case where the obstacle is a point, and then we will use that result to extend for general obstacles. For point obstacles, one can show the following result. It's a very technical result. So suppose that there exist constants b minus and b star, such that our potential function b is greater than or equal of b star on the risk region, and the potential function is lower by below by b minus on the safety region. So we need to assume that q on omega is a reference trajectory. So we need a reference trajectory to show the result. And if b star is greater than this constant here, where c and b are defined by these numbers that involve the interval of integration of the action functional, and a is defined in this way, then we can guarantee that any minimizer q on omega for J avoids the obstacle p with tolerance r. So it's a way to give necessary conditions in order to avoid obstacles based on how to construct how to bound the artificial function. So, but more concretely, we wish to give a tractable formula for the potential function. We wish to give a formula on how to construct the potential function in another way. For that, we can call a family of artificial potential parameterized by k, tau, and d, given by a function that depends on the distance between p, the obstacle, and q, the curve, an avoidance family for the obstacle p, where this quantity is a family of smooth non-negative functions that satisfy some conditions. Yes. So you can define the potential function as a function that is a smooth non-negative, parameterized by some constant that satisfies some conditions in order to avoid the obstacle, and depends on the distance between p and q. For an avoidance family of this type, we can compute the gradient of the potential function for the necessary conditions of optimality. Remember that we need the gradient of the potential function b. At this gradient of b can be expressed in this form. Oh, it's an easy computation. And in order to give a formula, we need an expression for the gradient of the distance between p and q. If we assume that we are in a geodesically convex neighborhood of p, we can use the exponential map, the inverse of the exponential map, to define the gradient of the distance between p and q. And then we can provide formulas for the potential function using that condition and the exponential function. So we will call obstacle avoidance feasibles with tolerant r if there exists a curve q on omega such that q is not on the collision region for all t, and using the feasibility condition, we can give a way to provide when every minimizer of J avoids p with tolerance r. Yes? And then we can use this result for general obstacles. So using the feasibility condition, we can work with some constants to design b, the potential function, to avoid the point p with tolerance r. In general, one can replace the distance between q and p with the distance from q to a set p. Yes, and the result still holds. So the gradient, computing the gradient, is almost impossible. Yes, but we can assume that p is totally bounded. If p is totally bounded, then we can cover p with a finite amount of balls of any radius, and then use the point obstacle strategy in each point of the balls that covers the set p to give the result of where we can guarantee that there exists a potential function b that avoids the obstacle. This is the result. So we have to assume that the obstacle avoidance is feasible with tolerance r, and then we can cover p with a sequence of balls and use the sum of each potential function to construct a new potential that avoids the obstacle p with tolerance r, using this potential function here. Other results that are related is extension to collision avoidance for multi-agent systems. One can define the potential function B in order to avoid collision between agents. And also, other application can be the interpolation of systems with impulse effects. That means hybrid systems. In hybrid systems, you have a continuous dynamics, a discrete dynamics, like walking. No, your leg is a pendulum, and when you touch the ground, there exists a discrete effect, yes, that you make a transition of the dynamics, and the floor is the switching surface, is where the transition occurs. And then we can use the point obstacle avoidance problem by avoiding the switching surfaces as obstacles. So in our GCI paper, as I commented before, we show the existence of global minimizers for a variational problem that is very similar to the one that I talked before, but appears this term here that is a measure to control the velocity of the system. Suppose that you are working with a satellite, and the satellite has a camera, and you want to observe what is happening around. An obstacle can be a star. You don't want that the camera point to the star, yes? So the point obstacle can be the star, and we want also that the angular velocity of the satellite goes slowly, because the satellite can be broken if you move very fast. No, this is a motivation to include this term here. Here dt denotes the Levitch-Beta connection on Q, and this is called variational elastic obstacle avoidance problem. The problem consists of finding a curve Q on omega, minimizing this functional, where B is again a smooth, convex, and non-negative function called artificial potential. And the solutions without the potential B, yes, are called in the literature explains intention, that we're working with Margarita Camarini in her PhD thesis. And this is the result that we show in the paper. So we use some techniques and analysis to show the existence of global minimizers. And of course, one can have necessary conditions for the problem that satisfies this equation here, are the ones as before, but with this term that involves the covariant velocity. And well, in order to relate with non-holonomic systems, one can add non-holonomic constraints to this problem. So in addition to this cost functional, you can have constraints on the velocities, and that defines a sub-Riemannian problem. And then one can study what means the Palais-Smell condition in sub-Riemannian geometry. It's to develop all the theory for existence of global minimizers using sub-Riemannian geometry that can be a relation with non-holonomic systems. As I commented at the beginning of the talk, this was not a talk about non-holonomic mechanics. I don't know why my paper was put in this session, but well, I wanted to say something about non-holonomic systems. That's all, and thank you for your attention.
Thank you, Leo, for your talk. There's some question. Margarita?
Thank you for your nice talk. Yes, I have a question related with the hybrid systems. Yeah. You didn't refer why you need to consider hybrid systems.
No, for instance, if you have now, hybrid system is another application. So instead of work obstacle avoidance for path planning, yes, you can try to think a related problem with hybrid system. That is a system that you have both dynamics, continuous and discrete. The transition between continuous and discrete appears in the switching surface. Yes, and then to design path plannings, maybe you can avoid the switching surface and go from one domain to another, because also in the formalism that we presented in hybrid systems, they are systems with multiple domains. The domains doesn't need to be the same, but you can go from one domain to another by avoiding the switching surface, treating the switching surface as an obstacle.
More questions or comments? If not, thanks again to the speaker.